So everybody, we are going to do enthalpy change of neutralisation, and I am wearing my favourite t-shirt again. Please put in the comments what do you think this means and why it makes sense. Okay, a beautiful word called alkynes here. Okay, and let's go on to go through a couple of those questions. So, enthalpy change in neutralisation is based upon the neutralisation reaction itself. So we add acid to a base. Neutralisation reaction is just an acid plus a base goes to a salt plus water. And our neutralisation equation is this. So that means every single time you produce water. So it's all based about this water production. Now, I'm going to show you the next question, which I've shown you in another video, but it's good to remind you. This is the type of question you might get in an exam. So which equation does not represent a neutralisation reaction? I told you about water. Okay, so generally neutralisation creates water, but it doesn't always create water. It's an acid and a base reacting together. So we can say that this is neutralisation because we can see water. We can say this is neutralisation because we can see water, but this one and this one we don't know because we can't see water. So all we have to do is look at those and say which one's an acid and a base added together. Well, that is an acid and a base. Acid and a base. Okay, acid and an alkali. This is a metal plus an acid. Okay, so therefore A is not a neutralisation reaction. So that is the main answer here. A is not a neutralisation reaction. Okay, now let's go and talk about the calculations and the enthalpy change of neutralisation. So the neutralisation of an aqueous solution of acid and base to form 1 mole of water under standard conditions. So this is the kind of thing we've shown you. Okay, and you can see there's your definition that you need to remember. And very important point, all neutralizations are exothermic, therefore your final answer for this, if you're working out the enthalpy change of neutralization, must be negative. Okay, and they're also going to make you assume that the density of all solutions are the same as for water. They're all aqueous, because they have to be aqueous because they're alkalis and they're acids. And they're basically, because they're all aqueous, you can assume, because it's mostly water, that the density is the same. So that means the density is 1. So that means the volume of 50 centimetres cubed is a mass of 50 centimetres cubed. The specific heat capacity of the reaction mixture are the same as for water as well. So that's in your datasheet 4.18. So if we carry on and we do a couple of questions here. So questions are based upon a polystyrene cup. So they're going to put them in a polystyrene cup to limit the heat loss to the surroundings. So here's your polystyrene cup, and usually you stir it with a thermometer, and it'd be better off if you added a lid here to limit the heat loss, but the polystyrene cup is there to limit heat loss, and that can be a 1-mark question in an exam, so make sure you remember it. Okay, so the polystyrene cup and the thermometer, and good to stir it with. And you create the uniform temperature with that stirring. Now we're going to use the equation Q equals mc delta T, or Cm delta T, which is the energy transferred Q, that's going to be in joules, really important, okay, and then the mass, which is going to be in grams, and then the specific heat capacity of water, which is 4.18, okay, and then the temperature change of the solution. Really, really important, okay, that you add both solutions together, because you can add 2 solutions, an acid and an alkali, so the mass of the solution is the 2 added together, but we'll go through that when you go through the questions. And as said, remember, all the reactions are exothermic, so this has got to be a negative number at the end. Now, here is your question, okay, and this is one of the simpler questions because it's a 1-to-1 ratio. Now, there's a lot of reading here, so stop the video and just read it. Okay, but I'm going to show you that most of this doesn't matter. Okay, so they've got 50 centimetres cubed of the sodium hydroxide, 20 centimetres cubed of the sulfuric acid. Okay, and basically what you've got here is actually a 1-to-2 reaction, not a 1-to-1, a 1-to-2. Okay, and this is a temperature rise of 3.4. So you calculate the enthalpy change of neutralisation for the sodium hydroxide reacting with the sulfuric acid. And again, you've got this assumption at the bottom. So we've got all that up on the side, and you can see it up on the side, and if you can do the question, please get on with the question itself, because I'm going to go over how to do it now. So, sulfuric acid, sodium hydroxide. Do the balanced equation first, that's really important, because you need to know this ratio here. Then you need to do the energy calculation. Now the energy, and then after the energy calculation, you need to determine the number of moles of water produced. So we've got this, CO delta T. Okay, and we've got our numbers. We put our numbers in. Notice we've got 70 grams. So if I go across here, why have I got 70 grams? Well, I've got 20 centimetres cubed here and 50. 20 plus 50 is 70. So there's my 70 grams in the middle. And the temperature change was 3.4. It tells you that. And it's a temperature rise, remember. And that also tells you it's a negative change at the end, exothermic at the end, because if the temperature rises, you get a exothermic reaction, which is a negative energy change because the energy is given out to the surroundings to heat them up. Now we need to determine the number of moles of water produced, and that's based on the limiting reactants here. And I've given you a nice one. This is why this is a bit simpler, is you've got that equation, you can work out the number of moles of the sodium hydroxide. So we've got the volume times the concentration. And then we've done the same for the sulfuric acid, volume times concentration. And we can see there's 0.1 and 0.2. So that means the sulfuric acid is 0.01 and the sodium hydroxide is 0.02, which means they're known as being in a stoichiometric ratio, which means the ratio is actually perfectly correct. So neither of them are limiting reagents because it's 1 to 2 and the ratio is 1 to 2 here. Okay, so we can use either of these to find out the moles of water. So if we use these moles of sodium hydroxide, that's exactly the same as the water because it's a 2 to 2 ratio. If we use this one, we have to times the number by 2 to get to the moles of water. But either way, 0.02 moles of water is produced. Then we do our final thing, is work out our delta H. Remember, it must be negative in the end. And we do the Q, which is 994.84, divided by the number of moles of water. Really important, of water, because it's neutralisation, so 0.02. And then you get a beautiful answer like this. Now, this is mostly where people go wrong. People go wrong because they've just forgotten to make sure it's a negative answer. And normally it's to 3 significant figures, and normally it's in kilojoules. So we convert it to 3 significant figures and to kilojoules. And that's how you do a reaction where you've got a stoichiometric ratio and you can produce enthalpy change of neutralisation. So here we have another question, okay, which I would like you to just get on with yourself. If you can do it, please do. Don't just watch me going through it. Okay, and I want you to calculate the enthalpy change of neutralisation. I know the question is not here. We're going to put that on in a second, but calculate the enthalpy change of neutralisation of all of that. Okay, slightly more complicated because you're going to have to use the moles to find out the limiting reactant and then base it off that. So we put that to the side, okay, and there it is. There's our question. Calculate it in kilojoules per mole, normally in 3 significant figures. All the densities are the same, but we've done that before. Here's our temperature changes. So what we're going to do, there's our temperature change. Just take the difference between those two. Okay, and all we have to do, literally all we have to do, is take out all the stuff we don't need and keep the stuff we do. So to keep that in mind, temperature change 2, maybe write that down. Okay, and then here's the stuff we actually need. So we start as we did on the previous one. Let's do our energy calculation. Energy calculation is here. So all we've done is taken the two volumes, 25 and 25, added them together, there's 50, and there's our temperature change here, and there's the specific heat capacity. And we've got our energy. Let's put our energy here. Okay, right, so we've got that. And then we need to determine the moles of water produced. So we're determining the number of moles of KOH. Okay, so KOH is up there, it's our alkali, so we've got that up there. Okay, and we've got 0.025 times 1. We've got those from the equation there. Remember, it has to be in decimeters. And then we do the same for the acid, okay, which is 0.01. Now, that's a little bit more difficult because the KOH, okay, so the KOH and that have a ratio of 2 to 1. Okay, so you're going to need to work out what is the limiting reaction. So there's lots of different ways of doing this, okay? So the way I do it, and the way many people do it, is just to look at that ratio and say, well, if I have 0.01 of the acid, I need 0.02 of the KOH because the ratio is 1 to 2. Okay, and I have more than that, so therefore the KOH is in excess. Okay, so the KOH must be in excess because I would only use up 0.02 of it, which means I must base my water calculation off the limiting reactant, which is the acid. Okay, so therefore, our water is 0.02. You might ask, why is that different to that? Well, that is the acid here. So let's get myself out of the way. Acid here, and the ratio of this to this is 1 to 2. Okay, so therefore I've just times 0.01 by 2. Okay, now, if that's the case, I've got my moles of water. Nice reminder just there about the neutralizations. Okay, and then all you do is take it, and you've got your final answer. Now again, I'm going to try and use different t-shirts each time. I hope you like this one. It's always going to be backwards, I'm afraid. That just adds to the intrigue. See if you can say what it says. Enjoy.